Hello everyone, I hope you enjoy our teaching lesson on transition metals. And without further ado, I'm going to hand you over to Calvin Chan.
Well, I'm going to start off with talking about transition metals. And in transition metals, they are in the D block, and the maximum electrons in D block is 10 electrons. And when you draw the electron configuration, the up and down electrons, there's two exceptions. One is for chromium, and the other one is for copper. For the chromium one, it's half 3D subshells and 1 in 4S subshell.
Sorry, I just got my finger over the camera.
Well, are we going to continue? Are you serious? Okay. For copper, it's full 3D subshells and 1 in the 4S subshells. Because the 3D subshell has a lower energy than the 4S, but it's more stable to have a full or a half 3D subshells. Now, there are two metals that are not in transition metals. One is scandium and one is zinc. Scandium is because it doesn't have any electrons in the D subshell, and zinc is because the D subshell is full. And finally, the colors. There's only 3 you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue. Okay.
Here we go? Yeah. So, after Calvin's excellent explanation of transition metals, well, I'm going to move on to complex ions. So, what is a complex? A complex is a central metal atom, which is a transition metal, with coordinately bonded ligands attached to it. So, a coordinate bond is a dative covalent bond, and this is where both the electrons come from the same species to form the bond. So in the complex, they're going to come from the ligands, which are the things that attach to the transition metal. A ligand is an atom, an ion, or a molecule which can form a dative covalent bond and can donate that pair of electrons. So that means it has to have a lone pair. So if you have one lone pair, this is called monodentate. 2 lone pairs is bidentate. So the number of lone pairs is going to affect how many coordinate bonds it forms. There are 2 common ones that you need to know. The first is ethane diorate, which is 2 carboxylic acid groups with hydrogen removed. And the other one is ethylene diamine, which is 2 amine groups on the end, with a lone pair of electrons in each of the nitrogen. So each of these form 2 coordinate bonds with the central metal ion. If there's more than 2 lone pairs, it's polydentate. So you've got different shapes of complex ions depending on the coordination number, which is the number of coordinate bonds on the complex metal ion. If you have 6 coordinate bonds, you have an octahedral shape. So this happens when the ligands are small, which is stuff like water or ammonia. The bond angles in this are all 90 degrees. The second type is when you have 4 coordinate bonds. Now these form a tetrahedral shape and the bond angle is 109.5. So these are just the same angles as your kind of shapes in normal compounds. There is one exception to it that you need to know, and this is when you have a coordination number of 4, but the bond angle and the shape isn't a tetrahedral. So this is when they form a square planar shape and the bond angles are 90 degrees, and the example they use in the book is cisplatin, which is 2 ammonias and 2 chlorines attached. And that's the end of your complex metal ions.
Thank you, Alex. The colors. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue.
Hello, welcome back. It's me again. Now I'm going on to colour. So, colour itself is your eye. Sir! Stop! We go.
Yeah.
Perfect. So, colour is when your eyes see EM radiation in the visible part of the EM spectrum. This comes from... Okay, no, start again.
No, but
So I was having quite a lot of trouble doing the colour section, so I'm handing you over to a man who's a little bit more knowledgeable on the topic.
So yeah, we're going to talk about the colors of metal complexes. Now, in metal, it absorbs the visible light because there's a splitting in the D subshell, and that's very important. You have to write that in the exam to get a mark at least. And then you have to talk about how the energy levels are specific frequencies, and also how the frequency has to be specific when the visible light absorbs it. Like the metal absorbs the visible light. When the metal absorbs the visible light, it also transmits a complementary color, and that color depends on, it's a complementary color, so if it's blue, it's orange. We also have to talk about the equation E equals HF. Now, if there are no 3D electrons or 3D subshells is full, then no electrons will jump, so no energy will be absorbed. But if there's no energy absorbed, the compound will look white or colorless. Yeah, that's everything about colors. The colors. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue.
Yep. So now we're moving on to transition metal hydroxides, which are coloured. So if you have a transition metal in solution, you're going to have 6 water ligands attached to it. However, if you add some sodium hydroxide or aqueous ammonia, then you're going to have ligand substitution taking place, and you'll get a coloured hydroxide precipitate. Now, there's lots of different formulas for this, which we're not going to show you now, but I'm just going to give you a brief overview of what happens. So, you are going to have 2 of the water ligands substituted for hydroxide ligands, which means that you're also going to have a colour change. So with copper 2, this colour change due to the ligand exchange, you're going from a pale blue solution to a blue precipitate, and that's the same whether you are adding ammonia or hydroxide. What you also get depends on what you add, so you'll get the substitution, you'll also get some extra water if you're adding the hydroxide, or some extra ammonium if you're adding the ammonia. If you add excess ammonia, the copper 2 metal complex will further react from the blue precipitate to form a dark blue solution. It re-dissolves again. With iron 2, you go from a pale green solution to a green precipitate, which is going to darken on standing. It's exactly the same process, just with an iron as the central metal ion instead of copper. With iron 3, you go from a yellow solution to an orange precipitate, which once again darkens on standing. Neither iron 2 or iron-free go on to form complexes with ammonia again, so they don't redissolve if you have excess ammonia. And that is pretty much all you need to know.
Nice.
The colours. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue. The colours. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue. The colours. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow.
So, your eye. Stop! And the other one is
The electron configuration, the up and down electrons. There's two exceptions. One is for chromium, and the other one is for copper. The colors. There's only three you need to remember. Iron 2 plus is pale green, iron 3 plus is yellow, and copper 2 plus is blue.
In the D subshell, and that's very important. You have to write that in the exam to get a mark at least.
and that is pretty much all you need to know.
Nice.